That brings us now back to the worksheet to make sure that we're on track. So the graph for the quantitation of protein by Bradford, we covered that. Small table to report the concentration of your unknowns. Include units, proper headings in the table. You should be able to do that. We covered how to calculate the concentration of protein in each of your unknowns. Write the concentration of myoglobin as determined by your Soret band absorbance below and include units. This we still have to cover. So if we want to determine the Soret band absorbance concentration, a little clunky the way that I said it, but you get the idea here. We want to determine what is the concentration of the myoglobin sample from the Soret band absorbance. And if you recall, we had a little table where we had equine, and we had bovine, and then we had the absorbance at 409 nanometers. Okay, and so you recorded this. The samples that you used here were diluted, right, into cuvettes, and each cuvette had 50 microliters of the myoglobin standard plus 950 microliters of buffer. And this was, right, kind of cuvette 3, if you remember this. All right, so we recorded the absorbance at 409 nanometers and zeroed the spec with buffer. So that was the deal here. Remember Beer's law. So the absorbance is equal to the extinction coefficient times, right, the path length, which is, for the cuvettes we used, 1 centimeter, and the concentration of the solution in the cuvette. In our case, we dealt with molarity, and our extinction coefficient is in units of per molar per centimeter. And when you do the math, all the units cancel out. So that means that absorbance itself is a unitless quantity. Okay, what do we want to know? We want to know the concentration. So we're going to solve the equation for the concentration term, and that is equal to absorbance over epsilon times B, which is our path length. And so I'm going to solve this for you using the equine sample as an example. So let's say that the absorbance was 0.312 in our cuvette. And remember that that was a dilution. So what's in the cuvette is the dilution. Where did that come from? It came from a concentrated stock. How much stock was it? It was 50 microliters. So we have 0.312 over the extinction coefficient, which in this case is 179,000 per molar per centimeter times 1 centimeter path length. And you can see that these cancel out. And then when we finish this equation, right, 1 over per molar is going to end up being molar on our units. So I just want to show you where that's coming from. And then let's do the math here. And we end up with 1.74 times 10 to the minus 6th molar. And it seems like there's also some issues in how to use exponents and the prefixes for the metric system. So this is also equivalent to 1.74 micromolar. So this times 10 to the 6th, we can express just using the character mu for micro. All right, so what is this number? This number is the concentration of myoglobin in our cuvette. Okay, so this is for the dilution. Let's
use our C1V1 equals C2V2 equation, where we have the concentration of the dilution times the volume of the dilution is equal to the concentration of the stock times the volume of the stock. And I'm going to keep color coding this so that you can trace it easily. Okay. What numbers can we add here? Let's try to get it all on one page. So the concentration of the dilution is 1.74 micromolars, and micromolar. And where did that come from? It came from here. The volume of the dilution is, right, if we say, well, what's 50 plus 950? There's 1,000 microliters total volume of the dilution. So the volume of the dilution is 1,000 microliters. And then what about this volume of the stock? Well, the volume of the stock is the amount of stock that was used to make the dilution, and that's 50 microliters. So that's shown to you up here. And the concentration of the stock is what we want to know. So if we do that setup, we have the concentration of the stock is equal to the concentration of the dilution times the volume of the dilution divided by the volume of the stock. And so when we do that, we have 1.74 micromolar times 1,000 microliters divided by 50 microliters. And when you do the math, you end up with 34.8 micromolar as your stock concentration. So when we go back and we look at this, right, we just did this. And you can determine that concentration for both samples, but we really only care about the equine sample moving forward to this next question. So in this next question, we're looking at a comparison of the concentration of the myoglobin as determined by Soret band absorbance, which is, right, we just did that, compared to the concentration of myoglobin determined by the Bradford method. And your answers are going to be different. So that's what we did kind of up here. Now, we have to do some conversions. And I'm just going to write it right here. So we're still working on this point right here. The Soret concentration is in terms of molarity, and the Bradford concentration is in terms of grams, essentially, right? So molarity is moles per liter, and really the Bradford concentration that you got out was mgs per mil. So we need to do some conversion of our units in order to make this comparison. And let's move down here. And let me show you how to get from this value in terms of molarity, right, or moles per liter. How can we go from this value to mgs per mil?
To do the conversion between moles and grams, we need to know the molecular weight.
And for myoglobin, for equine myoglobin, we're going to use the information provided by Sigma Chemical, which is that myoglobin from equine has a molecular weight of 17.6 kilodaltons, which we can take to be 17,600 grams per mole. Okay, so that is our molecular weight or our formula weight for this protein. And we're going to use it to convert between moles and grams. So let's move on and let's do some figuring here. So I have to move to the next page. So we have a concentration of myoglobin that is 34.8 micromolar. And we want to know what is this concentration in terms of mgs per mil. And to do that, we need to know the molecular weight of the myoglobin, which we're going to use 17.6 kilodaltons, and that is not an exact number, but it's what we're using. And so it's 17,600 grams per mole. Okay, so let's move this down a little bit. We have all of our numbers here. What does this number actually mean? It means that we have 34.8 times 10 to the minus 6th moles of stuff in 1,000 ml, right? Because that is 1 liter. In 1 liter, there's 1,000 milliliters. But let's just leave it this way. If we want to convert moles to grams, we can say in 1 mole, there would be 17,600 grams of the myoglobin. So this is going to tell us grams in the top part of our equation. And when we do that math, we find that we have 6.12 times 10 to the minus 1 grams of material. And again, that is in 1,000 ml. So what do we have? We have 6.12 times 10 to the minus 1 grams in 1,000 ml. Let's just clarify this a little bit. So this is 0.612 grams. So I wanted to get rid of that exponent. And now let's, we don't want grams, do we? We want milligrams, right? So we want milligrams. So how can we go from grams to milligrams? We're going to hop the decimal 3 places. So this is equivalent to 612 milligrams. And again, that's in 1,000 ml. So we've got 612 mgs of material in 1,000 mLs. And it just so happens that if we want to get rid of this 1,000 and go back down to mLs, we're going to hop the decimal back this way. So we have 0.612 mgs per ml.
So this is the equivalent concentration to this concentration. So we've gone from a concentration of molarity to a concentration in terms of mg per mil, and they're not going to give you the same concentration. And right, that's what we're looking at in this question here. So these numbers are going to be different. Why are they different? Because
there's a couple reasons it could be. So the extinction coefficient that was used might not be valid for the equine preparation of myoglobin, because I believe that that was calculated for bovine myoglobin. You might also have had some loss of heme in the preparation. It has to do also with how the Bradford assay measures the total amount of protein in the sample. So we're measuring the amount of protein based on a BSA standard. So there's, some sources of error there. But basically, you're measuring 2 different things, right? The Soret concentration, the Soret band concentration is dependent on the amount of heme. And the Bradford concentration is dependent upon the amount of protein. And so you're measuring this concentration of myoglobin in two different ways based on two different properties of the myoglobin protein. And so, you're not going to get the same exact number because you're measuring two different things by two different methods. And that's basically it in a nutshell.